Hello everyone. In this video, I'm going to talk about vibrations of simply supported beams. So if you watched my channel under playlist vibrations, you know I have a video that is vibrations of cantilever beams. And so to make this playlist more complete, I decided to talk about the simply supported beam. You know, cantilever beam and simply supported beam are two most common types of beams that you see. So the governing equation for both of them is the same because the relations that we used here between shear force, the bending moment, and the load is the same for both of them. So this partial differential equation that we found, where y of x of x and t is the lateral diffraction of the beam at location x at time t, this relation, this PDE, still valid in the system. That's the exact same thing, okay? No difference. The boundary condition is different. In a cantilever beam, what you have here is on this end at x of 0, y is 0 and y prime is 0, or the slope. At this end, where the bending moment is 0, y double prime, which is proportional to bending moment, is 0, and shear force, which is proportional to the third derivative of y, these are 0. So those are initial conditions for cantilevered. But for simply supported, your beam is pivoted here and there is a roller here. They cannot go up and down. So y at x of 0 and x of L at any time point is 0. And then because there will be no moment on a roller or on a pivot, and you know moment is proportional to y double prime, so y double prime is 0 also at both ends. Okay, so these are your boundary conditions. Initial conditions could be that at time 0 your initial displacement is f of x and your initial velocity is g of x. Okay, in general. So for these conditions, we want to find the solution y x of t, right? Y of x and t, and we want to do it analytically. So how do we do it? Here, like the video for cantilever, the technique for solving this specific PDE, this one, is to use the separation of variables. So I assume that my solution is the product of a function for only position and a function for only time. And I plug them into the original PDE. If I do so, then this is going to be the result of that. And now I can take one of these terms to the other side and divide both sides by f times g. So when I take them to the other side, now I'm going to divide both sides by f times g. And if I do that, then this f and this f would cancel, that g and that g would cancel. So on this side, you get this term. On the other side, you get this one. And now if you look, this is just a constant, which we're going to give it a name later. But this side here, this is only a function of x. And this side is only a function of t. And you can never find any function of t and x to be equal unless they are both equal to a constant number. So if they are both equal to some constant number, then yes, they can be equal. Otherwise, no function of t and x could be equal. So here we say both of them are equal to a constant. We call it omega squared. And why? Because if we do that, and here this one gives me one equation, and then equality of the left side with omega squared gives me another equation. And those are these equations that you can see: g double dot plus omega squared g equals 0. And f to the fourth derivative of f minus beta to the 4f equals 0, where beta to the 4 is basically when you set this left side equal to omega squared, look, when you set these two equal, then you multiply both sides by rho a and divide by ei. So that f to the f fourth derivative over f becomes this guy, and that one I give it a name, I call it beta to the 4. So that means f to the f fourth derivative equals beta to the 4 times f, or I can bring it to the left side, and this is going to be the resulting equation. Okay, so this is an important relation. That definition of beta is this: beta to the 4 is rho a omega squared over ei. there we go. So I got these two solutions. Now, why did we call it omega squared? In other words, we assume that whatever constant, we said both of these two sides should be equal to a constant, right? We said this is a function of x, this is a function of t, they are equal to a constant, but we assume that this constant is positive because it's squared. And if you watch that video where I discussed the two other scenarios, so if this constant is 0 or negative, then the boundary conditions will not be held, will not be valid. So you can see that. If this is 0, of course, that means that f to the 4 is going to be a fourth derivative of f is going to be 0, and then your f is going to be like a cubic polynomial or something, right, which cannot hold for these four initial conditions that you have. These four will not be satisfied for a cubic polynomial. If it's negative, if this number is negative, then here you get a negative here, and so the second derivative of g is going to be some constant positive number times g, and then the solution for that g is going to be some hyperbolic function. So this is going to be like a times sine hyperbolic of omega x and so on. And then plus like b cosine hyperbolic of omega x. And again, this kind of function will not satisfy those boundary conditions. So the only possible scenario is omega is positive. If omega is positive, then what's going to happen? If omega is positive, then when you solve for these two equations, this one, which is only an OD in terms of t, the solution of that, as you can see, is a harmonic function with frequency omega. And the solution for the x function is going to be also a combination of sine, cosine, sine, and cosine hyperbolic, but those sine, cosine hyperbolics are not valid in this case, so the only solution is just going to be, again, harmonics in terms of sine and cosine. But instead of omega times t, this is now beta times x. So these are the solutions for g and f in general. Now you have four constants to be found. C, D, H, and P. You need to find them. Also, this constant omega is something you don't know, and you have to find that as well. So let's see how we are going to do that. The first thing is, in this position function f of x, we know that y at x of 0 should be 0 at any time point. So if I plug in 0 here, this should be 0 at any time. And the only solution for that, since g of t cannot be 0 all the time, the only solution is f of 0 should be 0. So f of 0, plug in 0 in here, sine becomes a 0, cosine becomes 1, so you just get h. That should be equal to 0, and so that means h is 0. If h is 0, then your x position solution is just going to be this constant times sine of beta x. So the first boundary condition is satisfied. Now also, y at L should be 0. So if for x I plug in L, this should be 0. Again, g of t cannot be 0 in general, because if it is, then the total solution y is 0. That is a trivial solution. Since g of t cannot be 0 for all time points, the only solution is this f of L should be 0. Now here, in this solution that you found for f, you plug in L, so you get g sine beta L. This should be equal to 0. And clearly, well, let's make sure. I guess this should be P. So this is P, not G. P sine beta x should be 0, but remember, P cannot be 0. Here is the product of two terms. P cannot be 0. Why not? Because if P is 0, that H was also 0, that means the whole F is 0. And when F is 0, that means the whole Y is 0 all the time, which is again trivial solution. P cannot be 0, that means sine of beta L is 0. That means beta L should be an integer multiple of pi. N is an integer number. So if you solve for beta, you can see beta is going to be n pi over L, where n can be any integer number. So you found beta, but remember beta is a function of omega. So this beta, if you call it beta n, why n? Because it depends on the integer, because there is not one beta that fits this solution. There are infinitely many betas. So if you find the nth solution, beta n, which is related to, of course, omega n, this beta itself is n pi over L. So that you plug in here in place of beta, and you have to, of course, raise it to the 4. And here, from both sides, your goal is to solve for omega. Remember, omega is one of your unknowns. So there we go. Here we cross multiply both sides by EI. So we multiply this EI to the beta, which is this guy here, and divide by rho A, and then it's omega squared. So I take a square root. If I do that, guess what? I get this important formula. So here I found the nth natural frequency of simply supported beam. So if somebody says, what is the natural frequency of a simply supported beam? This is it. N pi over L squared, square root of EI over rho A. For instance, what is the first natural frequency? Just plug in 1 here. So it is going to be pi squared over L squared, square root of EI over rho A. There we go. Okay, so that is the first natural frequency of this simply supported beam. Then we have the second natural, the third, and so on and so forth. So this is the first thing that we found, the natural frequency. Then, if that's the case, then the Fn of x is, of course, because remember f of x is now this guy, it is going to be of shape sine of beta nx. And beta n, remember, beta n is n pi over L. So here, this is that beta n. Remember, your solution is sine of beta x, so beta nx, that is the nth solution for f of x. And if you want, you can add this p of n as well here. So, but p of n is a constant. So f of x here, sine of n pi x over L, this is your mode shape. So these are the mode shapes of this simply supported beam, and as I said, these are the natural frequencies. Okay? So mode shape number 1, for instance, is sine of pi x over L. Just plug in n of 1. Now, how does it look like? Well, if you draw the beam, this is 0, this is L. So at 0, it's 0. At L, it's sine of pi, which is 0. At L over 2, you get sine of pi over 2, which is 1. So your first mode shape looks something like this. And then as the beam goes up and down, then it comes to this. Right? So this is what the shape of the first mode shape is, right? These points on the beam, they go up, they go down, and basically this is the vibration mode. These 2 points are nodes, they don't move, and this is the shape of the first mode shape. Basically, this is how it looks like. So this is the first mode shape, and the frequency for it is this one. Then if you plug in, for instance, omega of 2, then omega number 2 is all you need is to plug in a 2 in that formula. So it is going to be 4 pi squared over L squared, and then square root of EI over rho A. And your second mode shape is going to be sine of 2 pi x over L. And again, it looks kind of similar, except the frequency is 2 times bigger, so your shape is going to look like this. Okay, and when this beam starts vibrating, it goes like this. So not only you have a node here and here, you also will get a node here in the middle. That's the second mode shape. And third mode shape will have 4 nodes instead of 3. It will have 4 with a 3 with a frequency that is bigger, and so on and so forth. Okay, so these are the natural frequencies of a simply supported beam. These are the mode shapes of the simply supported beam. Good. Now the question is, which one of these mode shapes and which one of these frequencies would you see in the final solution? Remember, your final solution is y of x of t. So which one of those mode shapes, which one of those frequencies would you see in it? The answer is it depends on the initial condition. Depends on how you activate the beam in the first time point. Okay, so for instance, if you make the beam something like this, a sine function, a half sine wave, since this one is exactly like the first mode shape, guess what? The only solution that you will get in y of x of t is going to be some constant, in this case 1, and it is going to be basically sine of the first mode shape, which is pi x over L. And in terms of the frequency, depending on whether you give it an initial velocity or not. For instance, if you don't give it an initial basically velocity, so make sure that, for instance, g of x is 0, but just f of x is non-zero, it's just like a half sine wave like that, then in this case, your g of t will only have a cosine omega term. This c will be 0. So it is going to be basically cosine of omega 1 times t. Like this. That's the only solution you would get. This mode shape, that frequency. Because your initial position exactly matches the first mode shape and you don't have any initial velocity. That is the only thing that you will get. If it exactly matches your initial condition f of x, if it exactly matches second mode shape, then you only get frequency omega 2 and second mode shape sine of 2 pi x over L, and so on and so forth. But if your f of x does not match any of these mode shapes exactly, for instance, you might give it a triangular initial basically displacement. That one does not match any of these sine waves. So you are going to get a combination of all of these frequencies and different mode shapes. Okay? And that is done by Fourier series, as I'm going to tell you in a second. One very important thing you have to consider is this. Whatever function that you provide for f of x and g of x, you need to make sure these functions will satisfy these boundary conditions, especially these two. Okay, so you cannot give it an initial f of x that does not go to 0 at the two endpoints. You cannot give it something like this, for instance. Say, hey, my initial f of x is something like this, for instance. Because here you have non-zero y, here you have non-zero y, and that is not possible. Whatever shape you give it, you have to make sure that initial shape basically has the y of 0 at both of these points. Okay, so it has to be anchored at these 2 points. Otherwise, it's not going to work. Okay, and the same thing for g of x. So here we say that if we gave it proper functions f of x and g of x, now this is my total solution. Why do I have infinitely many terms in my solution? Because I have infinitely many frequencies. Look at there. You don't have only one omega and one beta that matches your partial differential equations. If you look, you have infinitely many betas and infinitely many omegas. For all n's from 1 to infinity, each and every one of them will work here. Therefore, in your solution, your n should go from 1 to infinity, where this x function should be multiplied by the g function, so that f is going to be multiplied by these two functions, and then that constant p that you had here, if you call that p times c and p times d, if you call them q and r, or pn times c, call it qn, and Rn is Pn times D, call it Rn, then this is your total solution. This is your mode shape here, and these are the solutions for the time. Now we need to satisfy the initial condition. So now you say, okay, here, now I plug in t of 0, and for any x position, the solution should be f of x. So if you plug in t of 0, what's going to happen? This term goes away, cosine becomes a 1, so you will get summation of n from 1 to infinity of qn sine of n pi xl. This should be f of x, and now if you take a time derivative, this cosine becomes a negative sign at t of 0, that goes away, this sine becomes a cosine, that stays, this omega n comes out, so you get Rn omega n times that sine, that should be g of x. So now, you can, from here, you should be able to find q and r because f and g are given and this mode shape is a known function. And all you need to do is to find them by this Fourier series. So qn is going to be 2 over L, integral from 0 to L of f of x times the mode shape. And Rn is going to be 2 over L omega n. Why omega n? Because there is some omega n here, so you have to divide. Integral of g of x sine n plx dx. There we go. That's your q and r. So once from here, you solve for q and r and plug them back into the original equation. Guess what? Now you have the full solution. That's all you need to do. There we go. Now you got your full solution. So all you need is to perform these two basically integrals that are similar to the Fourier series. And now you have full analytic solution. Now, of course, you see your analytic solution can have infinitely many terms, or it could have only one term. That depends on whether this f of x has any overlap with these mode shapes or not. If it exactly matches one of them, then that one will be non-zero. The rest of them will be zero. Okay? But if this f of x is any other function other than these mode shapes, then these q's and r's, especially these other q's, will not be zero. G, that depends on the initial speed. Now you see that if initial speed is 0, so g is 0, then all the rn's, and rn's means the sine waves, all of them will be 0, so you only will basically get a cosine solution, a cosine term. Okay, so this is the analytic solution. And now, what about a numerical solution? Most of the time, you don't solve this analytically. In many software that you use, you can solve this using finite difference method. And in finite difference, you have to solve this original ODE with discretization. So you directly come to this and use finite difference on this. So you break down your beam into a bunch of elements, correct? So you break this whole beam into a bunch of smaller pieces. You call each one of them a dx, and then when you solve for the time, so let's say you go from time 0 to some final time, because numerical solution, you always need to solve it for so much time. So you give it a final time, and the way you go from 0 to tf is each time t is incremented by a dt. So each time, at each time point, you increment it by a time increment, and your elements are all size dx. And the important thing is this dt and dx, you cannot just pick them any random way that you want. So for instance, if I'm solving for 10 seconds, and this guy is 1 meter, can I, for instance, pick this dt to be 0.001 second and pick this dx to be 0.1 meter? Can I do that? is any combination of dt and dx will give me a stable, good solution, because what I'm doing, I'm approximating those derivatives in finite difference. Is any combination working? No. The answer is this. This inequality should exist between dt and dx. Here I call them delta t and delta x, but the idea is the same. So if you don't like it, call this dt and call this dx. So dt should be less than or equal dx squared over square root 6 alpha, where alpha is this guy, ei over rho a, and that is called the beam diffusivity, okay? So for instance, let's say this alpha is some specific number, just give it some number. So let's say, for instance, this is like 6, then your dt should be less than or equal dx squared divided by 6 times 6, square root of that is like 6. Okay, so if, for instance, you pick this to be 0.1, then your dt should be less than or equal 0.01 divided by 6. Okay, clearly this is bigger than 0.001, right? But this is something like this, for instance. So you get a 1, and then you get a 16 or 17, something like that. So as long as your time step is bigger than 17 thous or 17 milliseconds, your solution should be stable. For, of course, here an alpha of 6. If this alpha is a different number, then based on the step, the size of the element that you pick in the x direction, you should pick a different time step. Otherwise, your solution is not going to be stable. Okay, so keep that in mind. Here is the code that I wrote to show you how it is working for finite difference and analytic solution, and we can see both animations in the same graph. So here the beam is 1 meter long and the material is steel. This is the cross section. This is the moment of inertia. You can calculate the alpha for it, right? So in this case, your alpha is, let's see how much alpha is for this beam. It is 2500. It's a big number. So that makes your dt to be much, much smaller. I'm using 100 elements in this beam, so each element has 0.01 length. And then this number that I chose is even less than this threshold here. Because if you calculate this 1 over square root 6, so you can write this as dt less than or equal dx squared divided by square root alpha divided by square root 6, and 1 over square root 6 is approximately 0.4. So it's like less than or equal 0.4 times dx squared over square root alpha. And here I chose quite a bit smaller than that. I chose 0.05. I chose like 8 times smaller to get a better solution. And I only simulate the system for 0.1 of a second. Actually, you can go even further because the dt here, as you'll see, is extremely small. Okay, so you see your dt should be like 1.1 microsecond in order to do any good. So even 0.1 second is like a lot. So maybe I just show it for 10 milliseconds or so. Okay, and then here my initial velocity is 0. My initial position matches one of the mode shapes. And then here you're in basically enforcing your initial displacement. Okay, and then use the central finite difference theorem as finite difference formulas for fourth derivative with respect to x and second derivative with respect to t. And this is your update equation. That's the solution, the update. And then you enforce the simply supported beams. Okay. So here you have y and y double prime 0. For that reason, not only the first and the last nodes will have 0 displacement, but also the two nodes right next to them. So node number 2 and node n-1 will also have 0 displacement at any point, so that the double y double primes are also basically guaranteed to be 0. So you see here, this first node and the last node at any time point, their y's is 0. But to make sure that the curvature at the beginning and end is 0, I also force these two to also be 0. Because you can approximate y double prime by basically y of I minus 1, correct? And then plus y of I plus 1 minus 2yi divided by delta x squared. Now at this node, there is no I minus 1, so you can consider that 0. At this node, yi is 0. And if this guy is 0, that means your next node should also be 0 in order to guarantee a double prime of 0 at that location. So you're going to set this node to pin down and also this node to pin down. So the slope, the curvatures at the beginning and end are 0. And that's what we have done here. And then the loop is done here to calculate the numerical solution. For analytical solution, you have to pick how many modes, shapes you want to use. Because remember, your n goes from 1 to infinity here in the analytic solution. Let me show you. Let me clean this up a little bit. You see here, you're going from 1 to infinity. In practice, you cannot add infinitely many modes together. So here, instead of that, you pick a number of nodes, capital N, and the bigger, basically, modes you use, the bigger number of modes you use, the more accurate it's going to be. But again, here for simplicity, I'm only using 3 of them, especially because my initial position matches one of my mode shapes. So that makes life a lot easier. And then once you pre-calculate the analytical solution, then you're going to animate both of them in the same graph. And there is something interesting that you'll see here. So the blue one is analytical. The red ones, those circles, are numerical. You see they are both showing vibrations. And although the frequency of them is almost the same, or exactly the same, but there is a phase difference between them. You see that the numerical one is a little bit ahead of the analytical one, okay? So although they're showing the same amplitude, the same shape, but first of all, you have these kind of distortions here, of course, because you're discretizing it. You're not using infinitely many elements. You're only using, in this case, 100 elements. Okay, so the more elements you use, the more accurate this is going to be. But again, it is at the cost of a lot more computations. And the other thing is the phase difference. And that is the last thing I want to introduce to you. And now this needs a big discussion of its own. But in general, remember that finite difference techniques, they introduce something called numerical dispersion. Now, in this case, that means basically some of your frequencies, they will travel at slightly incorrect speeds, okay? Yes, so some of your mode shapes, some of your frequencies, they travel at incorrect speeds. So for this beam in this equation, basically it affects more the higher mode shapes and making them move a little bit faster than what they should compared to the analytical solution. So hopefully you learned something from this video. You learn how to analytically solve for vibrations of a simply supported beam, how to do it with finite difference. And then, of course, we are going to, I'm going to upload this file for you under video description so you can download it and look at it. And again, remember that when we do finite difference here, the update equation is going to be basically this. So this is the approximation of the second derivative of y with respect to time, and this is the approximation of the fourth derivative of y with respect to x. And here, the only unknown that you need to find is this one here. The value at any node at the next time point. Here, I represents the node number and n represents the time. Okay, so this n represents time and this I represents x. So using what you have at the current time point and the previous time point, at that node and the neighboring nodes at that time, and the delta t and delta x and the alpha, you can use this explicit update equation and solve for y of I at n plus 1 and keep that doing it in the for loop. But as I told you, there will be some discrete what do we call the dispersion, which is a wrong speed or a wrong phase between the finite difference or numerical solution and the analytical one. Thank you so much, and I'll see you in the next video.